Hey everyone, I'm Sudarshan. Thank you so much for coming. I'm the founder of Smallest AI. So today's topic is a little technical. Like we're gonna talk a little bit about the market. That's gonna last for less than 5 minutes or so, and then we are gonna focus more on uh, trends in voice AI more technically. What are we seeing in the industry? We are gonna talk about what we are doing. Again, like it's gonna be the technical depth is just gonna keep increasing with time. So just want to get a quick sense of what the audience comprises of. So who all writes code? Why coding doesn't come? Okay, who right? Who is an investor? Okay, and who is a okay, and who is sort of non-technical and just here to figure things out, etc., etc. Okay, awesome. Cool. So yeah, just giving you a preface. We will be sort of this talk is a little bit inclined towards the technical audience. So bear that in mind. If you have any questions, just wait for the end of it, and we'll answer all of it for you. Um, so I'm gonna jump right into it, and we're gonna talk about world models and world models for voice and what that even means. Uh, First, starting with a little bit of a market analysis, right? And today, if you look at voice AI, uh, so voice is a large market. There is a lot of companies that use voice in contact centers. These are humans sitting and dialing every single day, doing things like customer support, sales, and various other business processes. And yet, less than 1% of the market is actually automated. As you go higher in enterprises and as you sort of increase the complexity, it's even lesser. And so, even though there are a lot of demos that you might have seen where like voice AI is extremely natural and human-like, the penetration is actually quite low, and we are actually in the early phases of the market. And uh, we sort of study the market from a macro perspective. If you look at it, voice is not a new industry. It's stayed for, before I was born and so on. We break it down into four parts. So one is what we call voice 1.0. This is your IBR. So you press one, press two, and it will sort of guide you in the right direction. Then came voice 2.0. These are ML based bots, like you could say, hey, give me a refund and it will work. But if you say, give me back my money, it won't work because it's sort of indexed to the word refund. And 2023, 2024 onwards, there's been this generative AI based voice bots with ChatGPT, etc., coming in and voice becoming lower latency and more natural. So these are extremely natural. I mean, these make us imagine what like completely human like voice AI will look like. But there are still major gaps in sort of how humans speak and operate and think versus how voice AI operates. And so the big jump, we believe, and this is going to be the next way of voice AI, we call it voice 4.0. It's going to completely change how today's voice agents and architectures have been built. And we're going to talk about how and why. So let's look at the difference between how humans speak and listen and how voice 3.0 operates. So we call voice 3.0 is synchronous because in voice 3.0, you have these voice agents that first listen, then they think, and then they speak. So they're doing things one at a time versus human conversations are asynchronous. So humans are, as I'm speaking to you, you are already thinking. You might even interrupt me if I'm speaking rubbish, right? And you might be taking notes while I'm talking. So you're actually doing things while listening. And today, no voice agent in the world that is in production can do this. And that's why voice 4.0 needs to be asynchronous. And so we believe the future will be asynchronous architectures. So just by common sense, if you're trying to pass the Turing test, if you're trying to be better than humans in voice AI, you cannot do that with voice 3.0 just by common sense or logic. You will need voice 4.0. And so today, the series of lectures that we're going to talk about, we're going to speak a little bit about Hydra, which is our asynchronous speech-to-speech model. We had launched this 2.5 months ago. It's live with some enterprises. We are sort of rolling out to the public. And one of the key factors about Hydra is its thinking, listening, speaking, tool calling. It can do all of that at the same time. And we're going to talk a little bit more about how it does that. What are the architectural choices that we are thinking of? What are some trade-offs compared to current voice agents and so on? Um, some of the points we'll be touching upon are that Hydra is still using attention. Its attention has been a great architecture. It's not like something fundamentally new. What's changing is how you apply attention. Are you applying attention on the entire context, or are you applying attention on certain part of the context? Are you applying attention on sort of granular level tokens, or are you applying attention on latents? Um, and so some of these things allow Hydra to actually be way smaller than how LLMs operate. And it is also closer to how the human brain operates. And so it is sort of mimicking our behavior. And if you think about it, this is how AI should have been built in the first place, because text is not real. Like, text is man-made, discrete tokens that we have created in computers. Voice and video are real. These are real-world physical signals, and the way we process voice and video is how AI should have sort of been built from grounds up. But text was easy because of the internet, and that's why we started there. Um, so a little bit about us and the next speaker. So I'm Sudarshan. I'm the founder. My co-founder is not here. Apoorv is here, who leads our GTM. Arjun, who's going to be speaking next. He's our senior scientist and senior advisor and chief scientist. Samir, he's our lead research scientist, and he'll be speaking as well. So we have been sort of deep into the trenches, and Arjun, over to you to go a little bit deeper.
Thanks, Sudarshan, for the very kind introduction.
Oh, yeah.
I hope you can hear me all right. Awesome. So I'm going to talk about like my worldview of how I see these voice models evolving. So, like I'm calling it talk on real-time speech-to-speech models, how a machine learned to talk. And I'm Arjun. I am the CEO and founder of Fastcode AI. We are a Bangalore-based AI native services company, and we work with Sudarshan and others at Smallest on these cutting-edge topics. So, like Sudarshan was alluding to, I want to first make this point that audio is hard. It's harder than text. Why? Why do I say so? Any ideas, like from the audience? Like, does anybody agree or disagree that like raw audio, the signal is harder than text? So why? Because uh, audio has a lot more than text, right? So it has, let's say, tone, it has urgency, and there's like a lot of feeling that rides on, say, the signal that we capture from voice. And like again, Sudarshan briefly mentioned that we build AI on text first because text was firstly easy to scrape from the internet. And second, it was discrete. And I'll come to the discrete aspect of it in a bit. But then, it's tens of thousands of years of speech that we have evolved, our human brains have evolved over, let's say, about 5,000 years of writing. So when we capture audio, let's say when this microphone captures audio, physically, what do you think is happening? Separate. Sorry? Separate. Yeah. So essentially, there is like a diaphragm. The diaphragm is vibrating due to the pressure differences that my vocal cords are creating. The due to the air, and it's vibrating, and there's like voltage that is being captured at 16,000 samples per second. And that voltage is, let's say, correlated to the pressure difference. So this is how the speech signal is, and then the digital to analog to digital stuff, etc., is happening, and you finally get these 16,000 numbers in 1 second. So that is what your wave file will look like. Now, that is, let's say, speech. This is in some sense continuous. Of course, we have still discretized 8 to 60,000 points in a second, but still it's like a very fine discretization of a continuous signal. And text is, of course, by definition, discrete, because you have words and these words are discrete. And the way, I mean, so let's say the English vocabulary may have about 150,000 words, right? So you can then have a vocabulary over text, and this is why it's discrete. So with text, a model learns the words. With audio, it has to also learn the feeling. Now, what is the simplest way of doing it? Like Sudarshan briefly mentioned, the old school way, the I think 2.0 way, was to kind of create this cascade, as we call it. So we're essentially stitching these three models together. What are those three models? The ASR, the automatic speech to speech recognition model, the large language model, and the text to speech model. So any classic applications such as Siri, Alexa, Google Assistant was built on such a paradigm. And your ASR, the speech recognition module, could be something like Whisper. You could use any LLM, and then you would stick a TTS on top of that. Now, this is the old way of doing it. And what are the problems with it? The problem is of latency. So there are three models, three round trips. The emotion is lost because this is a mapping where it's lossy, right? When we are converting my voice to speech, we are losing signal which we can never reconstruct from it. It's like projecting, let's say, 3D to 2D, right? You will lose information. And then we use an LLM. So we've lost a lot of information already, and if this makes any mistakes, those mistakes are cascaded, so the errors compound, because if in any state it has made a mistake, there is no way to recover that. And lastly, there's like a lot of latency, right? So it's slow. So this is, let's say, the most obvious, the most direct way of solving this, and people did that back in the day. But then LLMs came about, right? So when these LLMs came about in 2021, we wanted to do speech by piggybacking on this LLM backbone. So people started to think, okay, how can we now leverage the LLM to also do this speech? And to do this, what we want to do is we want to discretize speech. And this video is about discretizing speech. So we use these codecs. Codecs is like coding, decoding models, and Mimi is one of them. And to kind of, I'll show you the video. Uh, so that's your speech signal. It makes these chunks. These chunks after the encoder then have a quantizer, a dequantizer, and then a decoder. And in audio, what they have is this concept of code books, and this is a learned code book. So this Mimi happens to be, and then there were, it's trained on other backbones, the Wave, LM backbone, etc. But the important thing here is that when we convert speech to these discrete tokens, it's essentially the ID, right, of the code book that you use. So this is the way to kind of discretize speech. And now, once we have discretized speech, once we have tokens for speech, then we can do a lot of things with it. For example, we can use it within the LLM. So the most, the basic models that people came up with were to say augment these large language models also with the speech vocabulary. So now you have additional tokens that came from discretizing speech. You enhance the vocabulary of your LLM, and now your LLM understands or can maybe even output these tokens, which now corresponds to speech. And those tokens can then be decoded into an actual speech signal. But if you do this using just an LLM, look what happens, right? So maybe the user speaks for a bit, and then it has to detect that, okay, the user is not speaking anymore, and then the AI model speaks, and then it again waits before the user speaks. So the speech tokenizer goes into the LLM, which is adapted for speech, and then there's a speech decoder on top of the LLM tokens. But the drawback is that it cannot listen to you while it's speaking. The model cannot, like, you can maybe build harnesses and engineering on top of that to kind of enable that, but natively it is unable to listen while it's speaking. You're unable to actually interrupt it, right? Because it'll finish whatever it was, let's say, going to speak. So this is what we call the half duplex model. It, when it, while it speaks, it cannot hear. And then the both at once is the full duplex. It speaks, it listens while it speaks. And the way this is done is essentially, you see if I have a picture of that. Oh, don't. Okay. So how it does is it essentially also, so now it has like two streams. One stream is of what the user is saying, and the other stream is what the LLM itself is saying, or the speech model itself is saying. And you can maybe interleave it, or you can just directly add those embeddings together, etc. But the whole point is that you now have two streams coming in parallelly, and you then, interleave them or add them, and then the LLM processes it in parallel. So Moshi was, it came out 2 years ago, 2024, and this was the first model to make full duplex actually work. You can interrupt it, it overlaps and back channels like a real conversation. It's truly interactive. Two audio streams modeled in parallel, and silence is just another token. So the heuristic is to kind of do this thing called VAD, voice activity detection. And that's just looking at like the amplitude of the sound signal coming in, doing some heuristics on top to kind of know if there is silence, right? But here, silence is truly modeled as a token. And the model is basic. So I'm going to show you a recording. The model is very basic. The voice is flat with very little expression. And it was a small research model, not built for products at scale.
Hey, how are you doing?
Hi, I'm doing great. How about you?
I was thinking, can you tell me something interesting?
Of course. Can you tell me about the history of the city?
What city are you talking about?
I'm talking about the city of Aleppo in Syria. It's a city with a rich history that dates back to the 3rd millennium BC.
Okay, can you now tell me a funny joke and laugh?
Sure, here's a good one. Why don't scientists just atoms?
Why?
Because they make up everything.
Yeah. So
Okay, now can you tell me a scary story?
Of course. Once upon a time, there was a little boy named Alex. One day, he found a door that led to a dark and ominous world.
yeah. So I mean, the point here is that the term turntable.
Okay, can you tell me the fourth planet in the solar system?
Yes, it's Uranus. It's the 3rd largest planet in the solar system.
No, I said, can you tell me the fourth planet in the solar system?
Oh, I'm sorry. I misunderstood. The 4th planet from the sun is Venus.
So, I mean,
Thanks.
it's a very small model. It makes mistakes. So knowledge is something that you can still test, and more about that on that later. But the turn taking was sometimes like too fast, right? Like it would like really interrupt you. And this was the first time people could make this kind of latency 200 milliseconds work on a round trip. And this is almost as good as human pacing. So it's amazing for a machine, but this is not how us humans talk, right? And this is maybe the demo from GPT Realtime from OpenAI. So let me first show you this demo and then we can talk.
Hey, how are you doing?
Hi, I'm doing great. Thanks for asking. Feeling chatty and ready to help with whatever you've got. What's up with you?
Nothing much. Can you tell me something interesting?
Sure. Let me think of a fun little nugget you can casually drop into conversation. Octopuses have 3 hearts, and their blood is copper based, which makes it look blue instead of red.
Can you tell me a funny joke?
Why don't skeletons fight each other? They don't have the guts.
Okay. Can you tell me the third planet in the solar system?
Earth is the 3rd planet in our solar system.
Cool. And can you now tell me a very scary story?
Late one night, you're drifting off to sleep when you hear your bedroom door click. You're sure you locked it, but now it's open just a few inches. You sit up, listening hard. No footsteps, no grieving.
I am right now standing 1 kilometer away from you, but so can you hear me?
I can't actually hear you the way a person would. No ears on my side. But I can respond to whatever you type or say through this chat, whether you imagine yourself 1 kilometer away or on the other side of the planet.
Uh, do you think I'm talking in a lower pitch now?
I can't actually hear your pitch from text alone. If you're speaking out loud, I don't have any way to sense whether it's higher or lower, unless you send actual audio and I'm able to analyze it. So for now, I'll just have to take your word for it, mysterious little voice friend.
Okay, cool. Thanks. Bye.
Yeah. So this is, the most.
Bye. It was fun chatting with you. Take.
Yeah. So this is like the smartest, most capable model out there, the biggest model. It takes about 1 second for it to answer, for it to come back. And as you saw, it still does not really understand what you're saying in the true sense, right? So the processing at the input side is still missing from even these huge models. And it essentially converts it into text, and that is what the model gets to see. So now I'll run a quick test, right? We're gonna listen to these 3 sound clips, each of 7 seconds each, and then I'm gonna ask you which one is like human and which one is yeah.
Well, because you told me now. That's the whole point. Come on, let's actually make a plan. You're not doing this alone, okay?
With a 90% reduction in turnaround time and an 80% improvement in planning efficiency.
Yeah, so the thing is, and I've been meaning to bring this up for a while now, is that, sometimes you just you space out a little when I'm talking, and it makes me feel like you're not really there.
So which one do you think was human? Sure enough. B. Who all B?
C.
Okay.
Very good.
Yeah.
Hello, robbers. Hand raised them. Like, why are you being shy? Like,
No, I mean, that's good because so we've come really far, right? Because I mean, are these models any good? I think they are very, very good in terms of how expressive they are. And this was Gemini. The second one was actually a human, but he was doing like a voiceover. And the last model, which most of you liked, was the smallest AI model. So I mean, I didn't do it on purpose, but this is I invite you to kind of check it out. Um, but yeah, I mean, there was a bias because it was also a slightly longer clip. Maybe the second one, if it was as long, it would have been a fairer comparison. But yeah, like, so, I mean, they're pretty capable. But the problem is that, voice evals are still very broken because we can measure intelligence and latency very easily. We can measure intelligence because LLMs have a lot of benchmarks and we can piggyback on those benchmarks to measure the intelligence of your model. Latency is, of course, easy an engineering, let's say, task, but whether it sounds human, this is like a really hard thing to do. So there used to be this MOS score, mean opinion score, and in there, humans were kind of asked to rate along, let's say, various dimensions, a score of 1 to 5. But then if you get humans to do all your data, this becomes really slow, tedious, time consuming, error prone. Also, then what people did was they were fitting models to this data and then kind of creating a model to do your eval. So this is the best way that people were doing. And the other way, which a lot of people are now doing, is to just use a multimodal model. So the obvious fix is to skip humans, feed the generated voice into a multimodal model, a model that also takes in audio, and ask it to score emotion, pronunciation, and the rest 1 to 5, like we were doing earlier. Now, there are a lot of problems again with this kind of an approach. One, because it hallucinates scores. Two, it disagrees with humans. So the Pearson correlation between humans, their scores versus what the LLM does was less than 0.45, right? So that this means that it's doing something which humans don't do. And really bad accent bias. So, for example, an Indian accent would get scored lower on quality, on content, on a lot of other things, which was clearly like an accent bias. So these are, let's say, problems which these benchmarks have. And, like the audio sample that we heard, it was pretty expressive, right? Some of us even thought that the third model is a human. But expressive is not the same as human interaction. If an AI is very expressive, it doesn't mean that we will feel the same that we feel when we interact with humans. So models are expressive enough that a short clip might fool you, but two things still give them away: understanding, it performs emotion without understanding it, and interaction. The voice is good, but the conversation is not. Real back and forth still feels like talking to an AI, because you will know that it's kind of not stopping when you're interrupting it, etc., etc. So interaction is a very easy giveaway. And sorry, hello, often. So
Hey, my dog just died.
that's Siddharth Sonokar.
Losing a dog hits different. It's not just a pet, it's family. That ache is real, and it's okay to feel completely wrecked right now. If you want to tell me about them,
Yeah. So, I mean, this was Grok, and it does feel like AI, right? I mean, you don't want to talk to an AI about maybe a dead dog. So, we're still like far away from where we want to be. And I think there is no one, let's say, ring to rule them all. I think you will never have like one giant model. What you need are levers with which you can dial the behavior per use case. For example, for a business use case, you might want higher intelligence, but it's okay for it to be less expressive, because you don't want it whispering or laughing or singing and so on. But for entertainment, you would want high expressiveness, but maybe intelligence can be lower if it's talking to, let's say, a kid or something like that. Reliable async behavior is where the next frontier lies, what Sudarshan was talking about. So thinking, listening, speaking, and calling tools all at the same time without losing accuracy. And finally, what Sami is going to go deep into is the world model for conversation. And this is where I think most of the interesting work in the next year is going to be. And scan this. I don't know if you can scan it from there. This is my LinkedIn if you want to connect with me. And yeah, like we're now, I think, at a point where we've almost taught them how to talk pretty decently, right? We like how expressive they are, but now we need to teach them how to interact like humans, which is an open problem. Thank you. Do you have any questions? Any thoughts, comments?
How close are how close are we? So I think this is exactly the question I was asking earlier. Is the voice AI models today feel very robotic and AI like, and generally in my family particularly, we start thinking and we have answers to if we are talking to somebody before the other person stops talking, which is probably good or not good in some situations. But for AI, voice AI, we are working on voice first product right now. How soon can we implement something like this in our product?
Yeah, absolutely. So you're talking about full duplex models, and I think Samir's talk goes deeper into that, and we wait for him to kind of answer your question.
Yeah, just like having said that, at least in our experience, even the cascaded models have become pretty good. So it's not like, I would totally piss on them. Like we see customers speak for 30 minutes with an AI sort of not understanding. Because if you ever gotten a call from a call center, that's pretty bad. Like the way the person's case. So it's kind of on the same, maybe slightly better than that.
Spot on. Awesome. Yeah. I don't know if it can come all the way. Yeah.
Thank you. I am still today the ability to convert speech to text is a big challenge, especially where there are accents involved, multiple languages that people can switch back and forth into. Without that, this whole thing will collapse, right? So it feels like very fundamental to what we're solving.
Yeah, so speech to text is a different problem. So, by the way, Smallest recently is at the top of the leaderboard. But the kind of models that I was talking about, you don't have this intermediate text. You're directly processing the speech signal, and then you take it to the LLM in the latent space, in the embedding space. No, you're not converting it into text. You're converting into a thought of text. So that's the latent space. That's not real text.
There fundamental issues between late versus the intelligence tomorrow, the people about it, then does it mean that Nathan's would be larger and how do you overcome that?
Okay, so you're asking if the bigger the model, the more intelligent it is. Yes, that's usually the case because you're riding on some LLM backbone, and the more parameter the model is, the more it knows, the more data it can retain. So yes.
Yeah, but I think one of the things we are also working on is LLMs are, I think, becoming better and better at like remembering things. So like if you think about human intelligence, you sort of, and it's more of a philosophical question. Is it about remembering more things or sort of quickly specializing to the task at hand? And so today we are storing information in the LLM layers. Should we store information in the LLM layers or should we rely on memory for that? And LLM should have some sort of an LLM or whatever AI that looks like. If you ever want to achieve, you would like should have peak telemetry. And so you rely on memory for information and models for intelligence.
On the call, the lights versus the size of the mall.
Yeah, I think so.
Can you repeat the question? This is weak.
As you could obviously it's not always directly correlated. You could have time to first open faster. You could have hardware acceleration take
Hi, when you respond, can you repeat the question?
The question was around
Like will bigger model always have higher latency?
higher latency and higher intelligence. Right?
Yeah. Yeah.
So, these models are not doing well. Like if you do species sweep model, the reasoning is very bad. That's why most of the companies have a hybrid system. And also with the tokenization system, you cannot give parallelistic informations or give more borders or like in other things. You cannot guess. So how will you improve reasoning and what are you going different from Moshi and other vendors?
Yeah, sure. I'll let you learn.
Yeah, so I think we'll wait for the next talk on reasoning, etc., etc. But I think broadly, we believe like there are like different directions of intelligence. Like if you look at what LLMs have done, which is like become really great at coding and taking up extremely long tasks and sort of doing it over multiple days or months, that's not like mostly how humans operate, right? Like humans are at least on a day-to-day basis, like we keep getting more specialized at the tasks we are found economically valuable for, and then we are optimizing to do them faster, quicker, better, etc. Right? And so one is we have been used to this thinking mode because that's what's popular today. But if you look at human intelligence, it is slightly different. And if you want to power this sort of real-time intelligence, thinking is something you have to offload to a offline model which can actually think and do those things. So even with a speech-to-speech model, you can actually offload things to other things. It's like, I mean, hey, my teammate is checking it, right? Like exactly like two people doing the job. And so that's how we see intelligence also. There's going to be a offline intelligence and there's going to be an online intelligence. Today we are here to talk about the online intelligence.
So Thinking Labs has also done speech-to-speech model, right? And I think their latency is a 0.4 high or something like.
That latency is pretty high. If I remember correctly.
No, it's 0.2. Yeah, it's still low. It is low with yeah, it was 0.45 seconds.
Is that or at least what we had tested was not not that. But anyways, like what we tested was pretty high, and also I think the model was also some 270 billion parameters and so on. And I think it's also multiple models. It's not like a single model that can sort of, do multiple things. And
So your model is smaller in size and
we'll speak about that. That's in the next. Yeah. And we also, I mean, we have sort of slightly different approach, etc. So Sunir will talk about.
If silence is a token, like does it like fill up the conditional? This like don't say anything.
Silence is a token.
Yeah. So, for example, there are two streams, right? And if the machine is talking, I mean, so for example, if the model is responding, so then you have that stream filled, but then the user is quiet. And what you might end up doing is just doing a point-wise addition of those tokens, right? Like after the inside the transformer. So, or you could just be interleaving those tokens within the transformer.
Yeah, so my question that does it actually fill up the context and then you have to like no, but not fill up.
So I just have to repeat the question. So you're saying, does it actually fill up the context? And
As in like, do we keep on doing the inference? Do you keep on doing the matrix multiplication like if specific text?
Yeah, but there are two streams, right? So there is always like either you're speaking or I'm speaking. So you will have some information.
Are you talking about full duplex models or?
Yeah.
Okay. Yeah. It's always on full duplex model for all these.
Yeah. So Kalvi, he says that like you project the internal sort of using the data in favor. How do you like debug in case a workflow does not do that? Right? Because mechanistic interpretability is still like
It's a unsolved problem is what I would say. We do, at least more probably we should discuss this offline. It's sort of a longer topic and definitely an interesting topic. Okay, so with this, handing this over to Samir. So Arjun spoke a little bit about sort of worldview and different, ways in which we switch from sort of building synchronous to now going to asynchronous voice models and voice evals and how they're broken, etc. Samir is going a little bit deeper into some of the asynchronous part of things and sort of how we are thinking of world models. Over to you, Sam.
Yeah, little bit about.
So my top will be a little bit shy because, results and with the chart. But yeah, I'll be answering Rashi's there.
It was
See. So can you guys hear me? Okay. So what I'm going to talk about, is an intermediate step that we took before I talk about like a more research topic that we are interested in, which is the world model for conversation. So what we are really after is a world model for conversations, a system that understands the dynamics of talking, not just the words. So the foundation we have built towards that is what I call a speech augmented language model, a model that listens to you directly and reasons with the intelligence of a strong language model. It can call tools and answer your queries, and is fast enough for a live real-time conversation. And over the next 20 minutes, I'll talk talk you from why voice matters and through how this model works and how it performs to the voice it speaks with and the full agent. And then we are headed next half of my talk will be modeling the physics of the conversation itself. So why is this becoming one of the most natural ways people use software these days? For example, asking for help while driving, changing a plan while walking through an airport, getting support in their own language. But a useful voice product takes far more than fast turn taking or a natural sounding voice. A real voice agent has to understand what someone means, hold context, recover when the request changes mid sentence, use tools while the conversation keeps moving, and respond in a way that fits the moment. So there are like three patterns that we have seen developers building around. Voice to action, the user describes what they need and the system reasons, calls tools and completes the task. For example, like find homes in my budget, avoid busy streets, book a tour Saturday, etc. And then systems to voice. So software turns live context into spoken guidance. So for example, your flight's delayed, but you will make the connection. So all three need the same thing underneath, a model that genuinely understands speech and can tease. So that's what we built layers. So before I go into our model, here's how the voice agents are usually built. So you chain these three models together, automatic speech recognition, which turns the user's speech into text, a language model that reads that text and decides what to say, and a text-to-speech model turns the reply back into audio. So this is a speech in, speech out model, and that's how most of the labs build it these days. But through these three separate stages. So the problem is in this pipeline. The moment ASR converts speech to text, everything in the audio that isn't words, for example, tone, emphasis, hesitation, and who is about to speak, is thrown away before the language model ever sees it. So all three models in a chains also stack up latency. So we change this stack. We collapse the ASR and the language model into a single speech augmented language model. It takes audio in directly and reasons on, with no transcription step in repeat. And also, we replace the plain text-to-speech with a conversational TDS that's aware of the dialogue and can listen back. So two speech-native components instead of three text-bound ones. So rest of the talk is really these two pieces. And let me start with the speech-augmented language model. So here's what it is. We add native speech understanding to a strong text language model. So the model hears the user directly and answers with reasoning of the underlying language model. So as we just saw, taking audio in directly keeps tone, hesitation, emphasis, availability of model. So that's the right design to work on. And four things to take away here: that it hears the user directly. So there's no middle step, raw audio in. There's no transcription stage that drops the information. And it keeps the language model's intelligence intact. So we add speech without degrading the model underneath. And it can also reason and poll tools. And we'll prove that on the benchmarks in a moment. And this model is actually used in production right now. So it has low latency, it's small, and I'll show you some results. So here's how the model represents a conversation. It sees a single interleaved sequence of audio and text, A1, T2, A3, and D4. The A's here are the user's audio. The T's are the model's text responses. So the user speaks, then the model answers in text, and then the user speaks again, and so on. The important detail is in how we train it. So the loss is computed only over the agent's text responses, the T's here. We never ask the model to predict the user's audio, only to produce a good reply. So, that keeps the training focus on thing we actually care about. And because everything lives in one interleaved system, both what the user said acoustically and what the model itself replied, the model always has full conversation history, which is what lets it stay coherent across turns.
Is a in a modality for open or
Raw. So now how do the audio and text actually get into the model? So a little bit more technical details. On the audio side, the raw waveform goes into a pre-trained speech encoder that turns it into embeddings, and the adapter compresses those further, down to about approximately 7 embeddings per second of audio. And that compression keeps the sequence short and the model efficient. which matters for latency. On the text side, text tokens come in through the embedding table of the backbone language model. So both audio and text become embeddings living in the same sequence. And the key point is that the backbone language model is completely frozen. So we don't retrain it. Its weights stay exactly as they were. That's why the model keeps its full text detections. And we are basically just teaching the model to listen, not relearning how to think. So freezing also makes training cheaper and more stable. So at the scale that we operate at, it's good for us, and it means that improvements to the base model carry straight over. So open source LLMs are becoming quite intelligent, and so whatever language model is released next, we can straight away use. And three things to remember from this slide: that 7 embeddings per second, one shared sequence, and a frozen LLM backbone. So freezing the backbone obviously raises a question like, if the language model is frozen, how does the speech model get good? The answer is knowledge distillation. So we have a large teacher model, a strong text language model that already reasons well, and the student, which is our speech model. And during training, the teacher supervises the student. The student learns to produce responses that match the teacher's, but from speech input rather than clean text. So the point is that this is a recipe for getting the intelligence of a large teacher into a compact speech native soup. So we are not fine-tuning the model and hoping that it stays smart. We are transferring the capability of the model's behavior into one that listens.
You repeat questions now, or like you want to interrupt you or no?
Yeah, sure. But
I'm just curious. So when you said are you guys using the Mimo encoder, or like is this like your own pretrained?
I mean, we are using some open source and not. Did you say Mimo? What's that?
Taiwan.
Okay. No. We are not using the Mimi encoder because its representations are actually very low level. So if you use the Mimi encoder, like it's very hard to actually keep the LLM backbone frozen. So you basically want to start with a speech encoder, which is already learning high level representations. So it's easier to bring down a high level, phonetics and lexical units and things like that, while also preserving. So, for example, a whisk, and if you're looking for a concrete answer, it's a whisper encoder. Whisper encoder also encodes not just linguistic information, but also paralinguistics. So, it's a good encoder to use for about connecting with the LLM.
Hey, Samir, can you repeat the question so that everyone will hear
I
it?
forgot one of those. So, yeah, what type of speech encoder are we using? So, we are not using any acoustic speech codec, for example, MIMI. We are using a speech encoder that is pre-trained using, for example, self-supervised learning or using ASR DOS.
Can actually go with the flow. As you pay
Like, depends on the.
But yeah, question. Said you are feeding a patty historically to a Yushma. Yeah. Actually, Yushma the us posted a
Yes. Not necessarily. So the question is like, the language models are supposed to take token IDs as input. Yeah, I mean, that's true, but the token IDs are converted into embeddings from the embedding table. So ultimately, like a transformer is just taking embedding sequence as input, right? So you can add any other embedding sequence to it. Like you don't need to actually have tokens. Yeah, so there's no speech vocabulary that we are expanding the embedding table with. So yeah. And that's what Moshi kind of models are doing. Like your Fury tokens, that you expand the embedding table and then, yeah. But yeah, this is a slightly different base. Okay, any other questions? Yeah.
Two questions. Yeah. For a pure words, languages are very different grammatically, even the structure of the language, the mean, and how people speak in the real world, we get the same language.
Yeah, like different accents, etc.
It's like might take some way people says. The second question is also in the real world. What be the reasoning part? Context. In learning from the system context. Right? Like I'm building for healthcare. I'm adding a lot of, right? So one of the things which is kind of troubling me is how we build for like using this kind of model. How do you, because people require yes, they are only going to bring us as when as voices are.
Yes. There are biases in these models. Yeah.
Yeah, older, especially older vision the way that's it.
Yes. Yes. So, that's a very good question. So there are two. So the question is basically like, yeah, the speech understanding part, and then yeah, how do you get the context into the model? Like what type of uh, industry we are using the model for example. So I think that part is simpler because if you have a very strong text LLM backbone, then you can probably prompt it with that kind of context, and people do that often. You might have to find you the LLM for your specific use case, and we do that internally also. But I think that's something the LLM can handle. Uh, when it comes to like a speech understanding, different speakers, different accents, genders, etc. I think that's definitely something. Whatever speech encoder you are using, you are kind of dependent on that, right? So if you actually recognize that, okay, there are issues with this particular age group or gender, etc., you can like fine tune your models on that data set. So I think that's the only solution I can.
Your models.
Our model currently supports, English and Hindi. But it is multilingual because the speech encoder that we're using is Whisper and it's like trained on a lot of languages. But yeah, it will have biases, etc. I think that's a good point. Like we should probably evaluate our models on those. Yeah. Okay. But yeah, I would also like to say like these type of problems everyone is kind of struggling with. So yeah, yeah, but good, great question. Yeah. So moving on, I'm on you on slide 8. So the model can think. Now it needs to speak as well, right? In a live conversation. So most text-to-speech systems synthesize each response in isolation. They take a sentence and read it with no memory of how the conversation has been going. So our TDS model is context-aware and multi-layer. So it conditions speech generation on both the dialogues or text and the user's earlier acoustics. So, three properties of this model is that it's context aware. It knows what's already been said in words and in sound. Its voice consistent. So the same voice and delivery across the whole conversation. So it doesn't reset its tone every turn. And it's low latency. It's continuous incremental synthesis built for real-time interaction. So, and if you have talked to voice agents for a long time, you might have seen that these agents sometimes change their tone, because they don't have information about the context. Oh. So the design of this TDS model is hierarchical with two levels. A backbone encodes the linguistic and the dialogue context and exposes its hidden states to a small local transformer. The local transformer generates audio tokens one after another. And then an audio tokenizer reconstructs the actual high fidelity waveform from those tokens. And the reason it matters is on the right of the figures. So text and speech are modeled at different levels, which lets the system take text in as it streams and emit audio out as it goes. So text arrives piece by piece. So for example, the weather is, and the audio frames stream out at the same time without waiting for the full syntax. And streaming both ways is what gets latency low enough to feel like a real conversation. And the model starts speaking before the language model has even finished the sentence. So that's the difference we found internally in our internal testing between a natural back and forth and an awkward pause after a return. So that's the whole model: a brain that can reason and a voice that speaks naturally and fast. So now I show you some results on some benchmarks and how does it actually perform. So one benchmark industry has been using for some time is called the Big Bench Audio. So Big Bench Audio measures hard reasoning over spoken input. And I show it two ways with the models thinking mode off and with it on. So I did not say that, but the LLM that we are using has a thinking mode as well. So with thinking mode off, we are at around 83% accuracy on this benchmark, ahead of GPT Real-Time 1.5 at 81, and well ahead of GPT Real-Time 2 with its like minimal setting at 70. So among the models that answer without eccentric thinking, we are at the top. And if we turn the thinking on, we jump to 96, and that puts us essentially level with the frontier models. For example, GPT Real-Time 2 on high thinking and Grok Voice Think Fast.
maybe one thing to talk about is the inky like really important for most sort of
No, I think for Big Bench audio is like asking you to solve like difficult puzzles, so you would probably never need for thinking mode for any real world voice agent scenario. So yeah, but it's just there because people measure on these benchmarks with this. So.
I had a question just on this benchmark. So this is just the smartness, but it seems like what you're focused on is kind of the feel, right? Like the how fast this, how it does. So
Yeah.
So I think it's a capture that you made off here because you could think more, you get a smarter result, but may not be the best.
So I mean, it was important for us to actually focus first on intelligence, right? Because if your model is not intelligent, like there's no point in being natural, right? It has to answer the things properly. It has to understand the context, etc. As one of the person asked. But yeah, there's this other eval that is more close to how a voice agent is deployed in the real world. And so here, here's the full agent, like how it's built. I have a diagram here. So user audio goes into the speech augmented language model, which produces a text response, and the conversational TDS turns that into a spoken reply. The user speaks, the agent thinks and acts, and the agent speaks back. So that's the whole loop. And the piece people generally underestimate is the layer underneath this voice agent, which is the orchestration layer. Right? It's basically what makes these two models behave like one agent. So it owns turn taking, knowing when the user has finished a thought, when to start speaking, and how to handle interruptions when the user talks over the agent. So without this orchestration layer, you have a transcriber and a voice, but you don't have conversation. So on this benchmark on AI EWF, it's a benchmark that was recently released, and there are a lot of industry models that are evaluated on this benchmark. So it's a third-party benchmark. We did not create it. So an end-to-end evaluation of the whole agent scored out of 300 on tool use, instruction following, and knowledge grounding. And our agent is competitive with the strongest voice agents out there. UltraVox is a couple of points ahead on tool use and instruction following. And GPT real time, is a little bit ahead than us on knowledge grounding. But we are right up there. And there's more things, the efficiency. So we are matching these systems at a fraction of their size. So let me show you what I mean. So this is the part that we care about a lot as scholars, right? Because that's our whole bet as a company, that the whole industry is racing in one direction. So scale the model up, more parameters, more compute. But we are trying to go the other. I think we believe that most of the voice agent scenarios can be solved with smaller models. And AIWF result I just showed you, comparable to the strongest voice agents, we get we get at only 30 billion parameters. So the model it's closest to UltraVox is around 600 billion parameters. So we are matching the frontier at roughly 1/20th the size. And it's why you can serve almost 16 concurrent conversations on a single H100. So it's also good for costing.
Just because questions they are asked in a voice. Yeah. Not sit there. Just questions asked.
I mean, it's not that they are dumb questions, but you don't need to solve like a math Olympiad question for. So yeah, but these models are still very, very smart. So for example, the Big Bench audio, is not easy. It has like very complicated long puzzles that you have to, comprehend the whole context properly to answer. So it is still very intelligent for sure. But yeah.
So basically, due to a specific.
No, not really. I mean, these models are pretty generic. Like, so the LLMs that we are using as the backbone, we did not really try to fine tune them on any specific distribution, like for getting good score at Big Bench Audio or anything. So these models are very general, and we are completely freezing them, right? And we are just attaching this speech interface to these models. So no, they are not fit specifically for a distribution.
About these, what those benchmarks, those these.
Sorry, was
This question.
yeah. Oh, sorry.
So, Apple game when you say.
Yeah, So basically, what he's asking is that why the 30 billion parameter model is good at these benchmarks, right? Is it that we fit these models to a specific distribution? But what I was saying is that the model that we are using is completely frozen. And these are open source LLMs that we are using. And they are fit on all sorts of data. Yeah. But yeah, what was your question again? On 633? Yes.
So good.
Yes.
Have you thought about like running this 30p? See other benchmark step, those 600 piece
Yeah.
or those easy ones.
Yeah. So, I mean, these benchmarks are what usually voice agents are actually evaluated on. There are some other benchmarks as well. But I don't think, uh, you know, so there's no like specific benchmark on which I would say 600 billion parameter model are run on to show their superiority. These are the benchmark that, like for example, Ultravox has been using for showing that their models are. So we are just using like whatever other people are using as benchmarks. But yeah, there could be, I guess you can design more benchmarks, to see like where the 30B model is failing. And like, because like it's reasonable to believe that, oh, there's 600 billion versus 30B, it has to be better at something, right? So yeah, that's good.
Just a philosophical comment.
Yeah, sure.
Right, what we have observed is the lyrics, then like Gemini, any of these here, right? In the real world, and they are fake, right? Because those benchmarks don't need anything for a Johnson and Johnson versus like Micron.
No, I think that's why. So what we are showing is that we are capable of building frontier voice agents. And obviously, like if it's industry specific, like we have to do more work. Like for example, we also have capability to fine tune models for yes, yeah, obviously, for sure, for sure.
Basically, the real value add is to build a kit almost that you can small like people can actually fine tune and put that these kits, whether it's accents, whether it's also the
No, but we are here for fine tuning. Yeah, I mean, you can give us your business and we'll fine tune the models. Yeah.
he also said discovery our problem. Yes.
So your model, with respect to the context of the memory, right?
Yeah.
So how long does it remain accurate?
So we have tested on like 30 minutes. Sorry. So the question is like, how long of a conversational context can the model handle? So we have tested it on 30-minute long conversations at least. I haven't gone beyond that, so I cannot answer that. But I think to like 30 minutes, I would say it remains pretty intelligent and smart. Yeah. Because all these because it depends on the LLM backbone, to be honest, like how much context can it handle. So yeah, it is pretty good, like these LLMs. Okay, I think I'll have to move on and then I can take more questions. Okay. So now the next part of the talk. So what we have today is a small, efficient voice agent that's competitive with the frontier. But I want to spend some time we're talking about like where we think the speech to speech world is going. And starting with how a voice agent works today, including the one I just showed you, it's a sequence of turns. You speak, the system waits until it's sure you have stopped, and then it replies, right? And then it waits again. Even the orchestration layer from the first half, like the end pointing, the turn taking logic, is really just machinery for managing these tasks. So, and there's a gap every single time. Pilot waits to be sure you are done. But that's not how people talk, as we have listened from Arjun and Sudarshan before. We don't wait for a clean handoff. So for the next generation, we want to get rid of turns altogether. So here's what we want instead. So take the things a human participant in a conversation on that when you are having a conversation with someone, and let the model do all of them at the same time continuously, not in turns. So listening never stops, right? The model takes in your audio the entire time, even while it's speaking, and thinking never stops either. It's always reasoning about the conversation and crucially predicting where it's going. So those two run continuously in parallel. And speaking and acting then happens the moment they should. Right? Notice the agent starts to respond before you have finished. And generally, human conversation have 0 millisecond of latency. Right? It's not even 200 millisecond because you have already started generating a response in your head while the user is talking. So the whole picture is asynchronous: listening, thinking, speaking, and acting, positioned independently in time and overlapping free. And that's what I'll say a conversational speech word model, which is just a fancy term for self-supervised learning and those type of concepts. Maybe you've heard of them. So let me make those four concrete as 4 channels. and sort them in what we already have and what we still have to build. So now I'll also lean on Moshi a little bit, and I show like what Moshi is missing and what we are trying to add to Moshi. So the good news is that two of them are basically solved. So listening in a streaming audio codec that turns both voices into tokens, and speaking is the conversational TDS from the first half. So we have those already. So the real work and the actual research that I'm trying to do is the other two. So we need to build a thinking channel that models where the conversation is going. So it basically models the trajectory or the low dimensional structure that underlie a conversation, right? And you can think of it as like a conversational physics. Taking analogy from video. So videos also underlie, a physics, a low dimensional structure. So similarly, conversations also have some kind of a physics that underlie the rules of the conversation. To make concrete what those two channels are, let me start from the closest thing that already exists, which is Moshi. And you have heard about Moshi a little bit. So Moshi is this model from Qtile. It listens, so it takes the user's audio in continuously and it speaks. It generates its own audio back in full duplex, so it can even overlap. So now Moshi also has what its authors call an inner monologue. So it predicts the text of its own speech alongside Dory. And it's tempting to call that a thinking channel. But it really isn't a thinking channel. It's just a second representation of what Moshi is already saying. So the words of its own speak sheet, right? There's no model of the user, no prediction of where the conversation is heading. So nothing is anticipating you while you don't. And there's no action channel at all, right? No explicit decision to speak, wait, backtrack, or interrupt. It is all implicit. So on our 4 channels, Moshi has to listen and speak, think and act, which means anticipating the conversation and deciding what to do or what's missing. And thus, that's what we are trying to build next. So here's our model drawn exactly the same way as I drew in the last slide. Same 4 channels, listen and speak carry straight over from Moshi. Audio is through the codec, audio out through our conversational TDS, and the 2 boxes that were dashed and missing a moment ago, we try to fill. So thinking is now a new channel. Instead of a text monologue of its own next words, think produce a latent. So a forecast of where the whole conversation is. So when you will stop, where you are heading, the prosody, the move. It's not text and it's not sound. It's a prediction in some abstract representation space, running ahead of you while you're talking to the agent. So we call that forecast a Z-hat. The words themselves still come from some language model backbone. We are not discarding the text knowledge, obviously. We are changing what the model does while you talk. And action is a brand new channel. So Moshi has nothing like it. It's an explicit, so this action channel is an explicit decision, whether it's a speak, wait, back channel, or interrupt, what type of move the agent should make next. And it reads the think channel's forecast and chooses, makes the decision of what to do. And speak channel is conditioned on both of these channels. So we have kept the 2 channels from Moshi and we are building these 2 channels. And the rest of the talk will be a hypothesis on how we can build these 2 channels. And I won't have any results for this. So this is how we build the think channel, and it's the heart of our proposal. And the key decision here is that we do not try to predict the next chunk of audio. So generally, like if you think about what Moshi is doing, it's predicting how the next 80 millisecond is going to sound. And most of the fine detail of what someone is about to say is completely unpredictable. And burning your modeling capacity in trying to generate it fully is completely wasteful. So we predict in representation space instead. A joint embedding predictive architecture, JEPA, maybe you have heard of this term, but you're adapting it to conversation and we are calling it conversational JEPA. And there are 2 paths in the model. The online path, which runs at inference. Take the conversation that has happened so far, both the channels of the conversation, and encode it. And a predictor outputs a Z-hat, an embedding of what's going to happen in the future. The target path is used only for training, which is a slowly updated copy of the encoder, but I won't go too much into technical details about this. But if you are familiar with, these self-supervised learning models, I think you would understand. But this target encoder encodes what actually came next in the conversation, and it encodes that into Z. And we train Z hat to match Z in latent space. So there's no waveform reconstruction and there's no transcript prediction. So three things that make this the right shape for the thinking channel. It predicts a representation, not a signal like a waveform. So it can be confident about the structure without hallucinating too many acoustic details. And it sees both speakers, so it models the conversation, not one term. And it's fully self-supervised. It learns from raw, unlabeled two-channel audio, which we have enormous amount of. 1 point on the scope. This is a short horizon forecast that the model is doing. So where the next moment is going, the turn boundary, the prosody, the trajectory of the conversation. And Z hat is essentially the most likely path in that trajectory. The conversation can, of course, go many ways. Deciding among those possibilities the job of the action channel, which we build next. So now the action channel is basically a head on this thinking channel that decides what the model does. It reads Z hat, the forecast, and chooses a move. 4 of these are about, the float, basically back channel, interruption, who docks when, and when to interrupt, etc. The fifth is a tool call decision that this action channel has to make also. So, reaching out to the world mid-conversation, so to look something up or to take an action. Pulling all of it into one explicit decision is basically the point of this action item. So in a model like Moshi, the question, should I talk, is just implicit in whatever audio gets sampled. And there's no notion of calling a tool at all. On supervision, I want to be precise here, like how do you get supervision for training this action channel? The floor labels you can extract directly from audio, but the tool call, you have to generate some synthetic dialogues with tool calls as labels as well. Yeah. So the open question is here is whether we train the head by imitation or by reinforcement learning. That's something we are exploring. But yeah, I won't have much to talk about that right now. So yeah, let me pull it all together and show how it runs at inference and why this is different from Moshi. So we'll read this diagram from top to bottom. The first channel here is listen. So your speech is streaming in and it ends where the dashed line is. So, where the dashed line says your turn ends. And the second channel is think. So this is our conversational JEPA channel. This is constantly encoding the conversation and forecasting the near future. And that's the dashed teal box Z hat here. And notice that it extends past the turn end while you are still talking. So the model can see the boundary coming beforehand. And the third channel is the act channel, which reads that forecast and it sits on wait in the beginning. But notice that that part way through, while you are still talking, it fires a tool call to look something up. So the answer is ready by the time you finish. Then right at the boundary, it flips to respond. And the speech channel begins to reply as you finish. So there's no gap day. And compared to the bottom strip, which is Moshi, Moshi is full duplex, can physically speak whenever, but it only ever emits tokens for the current frame with no forecast of where you are going and no explicit act decision. So in practice, it starts only once your turn has actually ended. So you get some small gap, like the latency that Arjun was talking about, 200 milliseconds. So I think I'll skip this, like I've talked about it enough. So we just saw that Moshi is missing 2 of the 4 channels that I was talking about. And the obvious way to get them, some people would argue, is to scale up Moshi as much as possible, like, GPT was scaled up to trillions of parameters. But our bet is that won't fix turn taking. Because turn taking isn't really, I think, a scale problem, is the objective problem, like how you are actually training the model. If you are training the model to predict all the atoms of your universe, which is conversation in this talk, I think you will have a really difficult time. And I think if you are technical, you have probably read the scaling law paper in speech LLMs. And if you look at the scaling law curve, it's not very favorable if you train your LLM on speech tokens. So in the first half, we bet that the structure beats scale on parameters, and we've got a 30 billion parameter age indexes with the frontier model. And in this half of the talk, we are betting that this conversational world model, which is learning this low dimensional structure of the conversation, will help us achieve much better intelligence than a scaled up Moshi style model. Okay, so finally has done. So we set out to build this voice agent that listen, reason, and act in real time. And here's where we landed. We added real speech understanding to a strong language model without giving up its intelligence, and we freeze the backbone distill into the speech part. And on Big Bench Audio, we are at the frontier, and I also showed you results on AIEWF. And we paired that with a streaming context-aware conversational TDS, and with the orchestration layer, the full agent is competitive with the strong voice agents. And hopefully, like maybe Sudarshan has some demo with our model, so you can also listen how it sounds. By mistake, I did not put any demo here. But yeah, we are not stopping here. The next step, as I alluded to, is this conversational speech world model. Instead of reacting token by token, it predicts where the conversation is going in a learned representation space and acts upon. And that's how we think we reach a speech that asynchronous and anticipatory conversation that generally, hopefully, feels you. So yeah, any issues? How do you answer? Yeah. Also, right. Oh yeah, you want a mic? Yes. Well, I'm sorry. So I wonder where you train this conversational model. Think about let me talk like stop trying to. Yeah, when you're trying to I can use bread right now. I can use bread later. Like, how do you, from the data and eval perspective, how do you define when is the good time to eat the bread, and let's say to RL design a with our function on top of the good interaction versus bad interaction. Yeah, I feel like this type of data very hard to find, and also very hard to measure. Yeah, I think I think still I don't have a good answer for that, to be honest. We are still trying to figure out how to evaluate. For example, if we build this model, we learn some kind of low dimensional physics of the conversation. How do we truly evaluate? Yeah, I think that's a open question for me. But yeah, sorry. It's more self-supervised. Yeah, we part your data. Yeah, but the question was like, if I'm like trying to understand your question better. But what if I not be interrupt? We are here now, or what's a good interruption? Yes, yeah, but yeah, what's a natural interruption? I think it's a similar kind of question. Like, what is a natural sounding voice? Yeah, but yeah, like, you have any? I mean, so I think the way we are thinking about a lot of this is from data, at least from me. And by the way, we are a team of very different opinions internally. We debate a lot about how we build this. Is not like I'm saying what Samir is saying, etc. Okay, so my thought process, at least, is a lot of this is gonna sort of come from data. Like, you could be a really annoying person who's interrupting me all the time, right? Or you could be a really patient person in which I'll sort of sleep off while talking to you, right? So you need it somewhere in between, and it's almost like designing a personality, and it almost goes back to Arjun's sort of talk around voice evals, because now you are evaluating a personality, and so you have to build data and you have to build evals that measure what success looks like for that person. Like, what you're going to need in a sales agent for voice is going to be very different from a therapist, right? And so you have to start thinking data first, and evals first is my opinion. I think that's a great point. Yeah. So basically, I would say this model that I was talking about is like a foundation model. Then you have to do some kind of instruction following, fine tuning on top of it. So that's when you can actually get different personas from this model. And some persona will interrupt more, some will be more kind and all that. So, yeah, then you need physical label something to label that you also need from what needs for one to do, and then you also need how you want to define like what's the outcome of this. Yeah, hopefully like next time when I talk, I can talk about those things. I think right now it's like, how do we build this foundation model that we can then instruction fight. Oh my god, yeah.
Yeah, I'd be find another question. So on the second part of the talk, you went over thoughts on what could be the future. I just want to challenge, like, how important is this latent reasoning, JEPA kind of better? Because I just as a baseline, you could, like a strong base.
So we already have baselines.
Yeah.
So basically,
But if I just complete my question there, like, you could play around with kind of delay, right? you could take a ground truth recipe, synthetically generate like a few conversations, and then, just have a model that learns, you could just add some latency, right? Some look ahead and delay to ground truth recipes and just work with the, the raw input data itself. Let's say it's the text of the next turn or a few seconds ahead or something like that, versus having this very, let's say, specific bet that you're going to have this JEPA style forecasting in the future. Because to your, thing that, okay, if you want to take the kind of scaling up data up to it now, language models also can plan in the future without JEPA stuff, right? They are kind of planning once you scale them up because they are predicting several tokens as a feature too. I just want to challenge that and ask you of why you made this bet then.
Yeah, I think question is, I think I sort of understand your question. But I would say, how do you rephrase? I didn't understand the question. It will be difficult to rephrase. I think a lot of things. But I think the rephrase is that, can we do this without JEPA? Can we? I mean, basically the crux of the question is like, can we just do GBD on tokens and do this sort of thing? And so I would say the baseline there is Moshi. So Moshi is a baseline. It's a 7 billion parameter model, and it's actually really, really bad at turning. Right? It like does not understand when to interrupt, when to back channel, etc. Like it has some capability, but if you actually talk to it, it's like pretty bad. So I think the speech GBD, if you will, right? The GBD models that are trained on speech token, as I was saying, that scaling laws are not that friendly when speech GBD models, right? Like there are papers studying like how good these models are at learning abstract structure if you train these models on audio tokens versus text tokens, right? So when you train these GBD like models on text tokens, they are much faster at learning abstract representation than the speech language models. And those speech language models are actually trained on pretty abstract tokens already. But Moshi is training on very, very fine tokens. It also has the acoustic and the semantic tokens. So I don't think you can easily scale up these models to learn all this behavior internally. That's what Moshi is trying to do. But like our bet is that you cannot do. Like you'll have to basically scale up maybe quite a lot. You'd probably need a lot of data. And that's something like we don't think is the right path to, getting that kind of intelligence in like a speech GPT like one. I'll say that.
I'm curious, like, Hydra compared with NVK's with the module, like across module, the Edge Flamingo, the new metro, Nematron. That does 30 billion hybrid as well. The small one.
Yeah. So Nemotron, is it I mean, I'm trying to think, like, is it
This one is persons. The sort of so
But this is a new one. Okay.
Secular lab. That's not. Right, the first was the they did release an ASR model, but I don't think.
Yeah, they have ASR models, and the Nemotron model, I think, is a LLM, as you say. But yeah, Personaplex is pretty good at like you can control how the voice sounds. So if you want a call center agent, etc. So they did those, but they did not fix the physics problem. Like it's still pretty bad at turn taking and all the things that I was talking about. Yeah.
When you're determining how small a model should be, that is generative, how did you land at 30 billion is the one, right? Because at the end of the day, if you're creating a generative small model, it doesn't matter what persona, what industry, what context. Sure. That's a purely fine-tuning problem. But this is a fundamental, foundational, getting to that level of accuracy, performance. So it can be fine-tuned to multiple contexts. So what is the trade-off you ended up having to make, either on the latency or the accuracy or the level of ability to fine-tune on top?
Yeah. So I think one answer is that empirical, that we tested a lot of open source LLMs as our backbone. And we found like a happy medium is around 30 billion parameter dense model, gives us like good performance on all the benchmarks that industry cares about and they care about. So the trade-off here is obviously the bigger your LLM backbone is, the better it is, the easier it is to control its behavior. So, we saw also in our internal testing that sometimes I would say I would have to give it up for the larger models that, they are easier to control and you can give more complex system prompts, for example, to get the behavior that you want. So, there will be some trade-offs. But I think we are happy with this, the size that we have right now. And yeah, we are also like testing with some clients as well. And yeah, we are able to solve most of the use cases.
Do you think that would apply to the two other channels that has been created, which are really more the thinking and acting channel, which seems to be the most critical ones according to me? Do you think, given your base assumptions here, would affect that next two channels?
So just sort of long story short, we don't know. Okay, it's not like we know. So this seems to be the best, but there are a lot of directions and bets which we have not talked about in this talk. But one of the things one of our researchers had been working on was continuous learning and sort of that in his previous life. And uh, there we have seen that smaller models can actually adapt faster if enabled continuous learning and so on. So there is a lot more, and we don't think 30 billion is the right size. It's just where we are right now. So
Yes, and that's right. Yeah, that's a fair point.
Yeah. I have a question about the hallucination. Are you observing the hallucination? Because I can imagine some scenario that, so in the speech understanding part, for example, if I'm talking to the your model and someone close to me say something, so does it add it to, is it added to the model context and you see some hallucination?
Yeah, definitely. If your speech input is very noisy, like that can happen. And yeah, we are actively working on solving that issue. So yeah, but that's definitely a real issue.
If like intentionally I stop speaking and someone else come into the conversation and say something, does that model can see the speakerization part?
Yeah, we have front ends that are trying to do like target speaker extraction. So we do try to solve some of these issues, but yeah, it still can be a little bit brittle. Like if it's too noisy, it cannot solve like all scenarios. But yeah, we have front ends for our voice issues there.
yeah, I mean, there is definitely an interesting direction of like, should a voice to voice model speak back when, let's say, there are two or three speakers? Like, imagine like you're in a meeting room and like people start talking amongst each other. Like, do you also want to keep replying or like, hey, take a step back, etc.? So, those are challenges, etc. That, I mean, right now we are more solving for primary speakers, is what I would say. Like, we don't want to complicate the problem with secondary speakers. We treat secondary speakers as noise and sort of try to remove secondary speakers. I mean, we train the speech encoder such that the it's robust to secondary speakers, noise, etc. But we are not training intelligence on sort of which primary speaker to respond and when to respond. And like, I think that's something you can train on.
Even for the primary speaker, if the audio quality is not good, so it would be hard to capture the tone and some expressiveness in the audio. So
Yeah, I mean, so these models, these speech encoders in particular, they are quite robust to, those type of like packet loss, for example, or noise in the audio. They are trained like that, right? Like they're trained with a lot of noise augmentation, etc. So I would say like these models are pretty good at extracting the right representations, even if the audio is very noisy. But yeah, I would say like probably a better benchmark is needed for testing that, but that's just my hypothesis. Yeah.
I had a follow up to that. What about mod AI to human reaction? Can that be something in my ears that will work? It's still a meeting type of setup, but
Multi-body.
cut to AI one.
I think the AI does not treat AI as AI. Just treat it as another part.
Yeah. So right now we are, I would say, focusing on two-party conversations, but not multi-party. That's like another level of difficulty for sure.
How much data did you use, or was you using most of it? What's the rough split?
So for the speech augmented language model that I showed you in the first half of the talk, it was pretty minimal data because you are not fine tuning much, right? You're only fine tuning the adapter between the speech encoder and the text emitter. So I would say like on the order of like 10,000 hours.
Did you create in-house or externally?
No, it's like we are using open source automatic speech recognition data sets, and then we are transforming them so that it can be used for training on.
And you have vendors as here. See, your looks.
How much synthetic data ways to like corporate? Essentially, like the action taking generate in.
So really built up product. I think that's something we haven't done yet. There is a thing that we are working.
You publish your model price.
Yeah, for another. Currently, the is manufacturing. Years. I you can validate that based on all layers.
All. Yeah. Phone models. Yeah. All combined is around 30 quarters. But the XLM backbone is around like 26, 27. So yeah.
So you are basically one of the predicting offices. Yes. So sorry. Oh, yeah. Boss. Hi. Yeah.
I have a question on how the human interjects while the model is asleep. How do you deal with that?
So right now, the model that is in production, when the human interchange is just like a simple voice activity detector based model. So it's basically just looking at the voice activity in the user's channel. And if the user speaks, then the agent stops. So it's a pretty simple, but you can do some graceful things like the agent doesn't stop, suddenly it trails off and things like. So that's the engineering around the voice agent.
And I've also seen a lot of voice models that require the user to wear a headphone or an earbud so that when it speaks, it doesn't think that the user is speaking back. So that the sub model.
Oh, this is the.
That's not a problem because I mean generally, yeah.
I mean, that's not a problem, at least for us, because like your laptop is giving out your audio through a different channel and takes in audio through a different channel. So it does not, like in your meetings, you don't like hear back what you are saying. Like you echo.
I had no other translation. You can do a cancellation by.
We don't need to. Right? Like, why would we need?
I'm just curious because I've seen a lot of voice models that have this problem where you have to wear headphones, otherwise it won't work properly.
That's the hardest part.
It's basically the problem is acoustic echo cancellation. And depending upon what kind of browser, phone, microphone combo you are using, it's a hard problem. Like I found out, like I was at another voice AI setup. Perplexity has a dedicated AEC engineer just for acoustic echo cancellation because the number of problems, unless you have a dedicated app in which you control your AEC, you're left to the hardware on Apple, and Apple keeps changing their OS, and you are left to the mercy of Apple on Microsoft or Dell or Lenovo or Samsung or whatever is the device and the browser working.
Yeah.
Unfortunately, that's the real world of it.
Yeah. So long story short, like we operate at a layer lower. Like we treat that as a problem we should not get it to. It's a more of a hardware and sort of application problem. The whoever adds the voice model as an interface into their application has to solve.
How much are you relying also on your own development versus already leveraging just the flow? 11 Labs, I'm brilliant. I use all of them. So, like, do you need to reinvent the wheel or like completely take different?
We don't want to reinvent the wheel, so we are definitely relying a lot on the open source text LLMs. But everything to do with audio, I would say we are building in house. So
Can I ask a question on the act part? Okay. So you mentioned that the goal is to make these things more asynchronous, right? Going back to the goals of the talk. So, have you considered like basically calls to the thinking LM? Because right now, if I remember your slide correctly, it was just like generic tool call and like whether you should interrupt or wait or something like that. But you can imagine that there's like a handoff, right, between the talker and the thinker that is maybe doing more complex stuff with your back.
So I think what you are talking about, obviously, are all the issues that will arise, once we have something, working. But I think we have thought about it, but right now we are at a much earlier stage.
So the focus is on the naturalness then,
Yeah.
not so much the smartness, because you could go either of two ways.
So that was the smartness is still coming from, yeah.
No. I think we are confusing the smartness in real time with the smartness offline. So the tool call abstracts out the thinking, right? You could tool call to a thinking model, you could tool call to a database, you could tool call to anything, right? And what this model just cares about it is someone is gonna do it, right? Like someone or something is gonna do it. Now you could call it a thinking mode, etc. But this model still
responses, but which has to come in somewhat in the middle. Like let's say,
yeah. So that's why the tool call is asynchronous, right? Like it's not blocking the conversational flow. So this model still has to act, but the sort of intelligence of this model is different than the intelligence of the offline model, which can obviously do various things. I mean, it need not be a model, it could be a API, it could be anything, right? So definitely the reason this is built this way is we see this evolving into a multi-agentic system, right?
So what hard did physics solve, taking a very physics approach compared to almost everyone's doing?
So the main part that physics is solving is turn taking, I would say. I think that's the major problem in voice agents. So I think Moshi, these type of models are not really able to learn that low dimensional structure. So I think this could be a good way.
Did it actually then directly impact the learning capability itself of the underlying 30B model?
I don't think so, but it will impact the learning capability of Moshi, for example. Like if you add these extra channels to Moshi, then Moshi has to do less work in learning all these low dimensional structure, right? So it could make Moshi respond better, I would say, because it can then focus on like reconstructing the audio tokens, more fit. I think that's something I was thinking about.
This considering the previous question I had regarding interoperability of build. How much of it is like collapsed into like say a unified model similar to what like thinking machine has done? Yeah, versus like say this is more like a harness or an orchestration layer where you have sort of visibility into like say when it goes into thinking mode or when it offloads to another sort of exterior service. Is it like has it been all collapsed into a model or is it still you're still operating at some abstraction?
There's still a text evidence. Okay, that I did not show. Like, yeah. You had something? Yeah.
No, so there are multiple frameworks, but I think particularly with respect to, I think your question was interpretability of the latent thinking space.
I said like also like because there are like say 4 different channels, 4 different sort of actions going on simultaneously.
Correct.
You have visibility into like say when it does a particular sort of like either like say a tool call or a acting mode. Or
I think you can definitely build it with a very high confidence interval. Like you can build it to behave in a certain
probabilistic, but not
it's probabilistic but not deterministic. But more importantly, particularly that latent interpretation is something which is, I would say, unsought. Like you understand the results because you know the model is doing great, but you don't know what that latent thinking is. Like it's like trying to observe your thoughts. If that's
How heavy lifting orchestration will become going forward? Because there's one challenge, anything small, heavy orchestration kicks in, multi-agent, same issue. And the real complexity kicks in there, and even though the model has achieved its performance. So where you index more as you move towards the next 2 channels?
So I think if I understand your question correctly, yes. I think for me, I feel like orchestration is the biggest problem that is unsolved. So I think this idea is kind of actually solving for that. So yeah, I think most of the effort you would see in the future, I think going on the orchestration there for sure.
So I think we'll take a break. We'll sort of mingle now. Just sort of ending notes. So our team internally has various definitions of ready for production. Okay. So in case if you guys are at like a slightly higher voice volumes, we are sort of giving you sort of early access to some of these models. The SALM model is sort of public and live. You can use it. Everyone can use it. But if you also want to sort of test out Hydra, etc., reach out to me directly. Would love to understand your use case and sort of implement. But yeah, with that, opening up the floor, just if you guys have not had cold like pizza, now it's cold, but you can still have it. Otherwise, enjoy the drinks. Feel free to talk to folks one on one. Thank you everyone for coming.
Thanks. I don't think that is so. My page up, yeah. Sample, right? So, yes. You need to see. Please. Oh, you can give it back here. I think. Yes, it was like very happenstance that you got to be. It is, yes. See, you're like a listener. It's a hat. Cool. Oh, but you tell you the too. But you up. You only didn't give me a number. And I can really. My last job, I was telling a lot of. He's knocking you off. What do you think? This slow. You wait. You know what it means in Hebrew?
No, I have no idea.
It means my name. Ishi.
Oh goodness. No, that's just my name. We actually just launched a bunch more team.